Hello. Today I'm going to be talking about my research as part of the Carnegie Mellon University Robotics Institute Summer Scholars 2020 cohort. My project was to develop a destination-aware auction system for paratransit scheduling. Paratransit systems are like Uber Pool, with flexible pickup and drop-off locations, but they are government subsidized and serve the special needs populations, such as the elderly and disabled. Because they are government subsidized, it is especially important for paratransit systems to efficiently utilize all of their resources. Paratransit scheduling, abstracted as a vehicle routing problem, has already been solved using auction-based systems. However, in these static systems, all ride requests are known upfront and cannot accommodate any last-minute or real-time requests. In addition, these systems do not take into account that the time costs associated with each request are destination dependent. Our research will address these by accommodating new requests dynamically and weighting them based on an assigned priority value. In our work, we start off with a standard auction system. When a new request is submitted, the control center sends out a message to all of the vehicles asking for bids. Each vehicle responds with its own bid, calculated without knowing the other vehicle's bids. The control center then selects the best bid, which in our case will be the smallest one, and it will assign the request to that vehicle. The key part of this process is how each vehicle computes its bid. In our system, the bid is actually a function of the cost, which we want to minimize, and so the smallest bid will be the winner of each auction. To compute its bid, each vehicle will create a hypothetical schedule with the new request added. It will then compare that to its current schedule and take the sum of all the additional delay caused to the requests already assigned to it. These schedules are created by solving instances of the traveling salesman problem. This is a well-known problem which, given a set of locations, tries to find the shortest path to visit all of the locations exactly once. We used Google's OR tools to generate these schedules within our constraints. Each request needed to be picked up no later than 45 minutes after the requested pickup time, and no ride could take more than 2 hours. Additionally, we also needed to make sure that the vehicle that a request was assigned to was equipped to accommodate any disabilities of the passenger. To make our system destination aware, we assign different priority values to each request based on their final destination. If it is important that they arrive at their destination at a specific time, such as a doctor's appointment, then that request is assigned a high priority. If their destination is somewhere where they should be preferably on time, but it is not critical, such as a friend's get-together, then that request is given medium priority. If they're going somewhere where it is not important that they reach by a specific time, such as to the grocery store, then that request is given a low priority. These priorities were used to determine the order of the functions mapping the computed time costs into bids. Low priority requests used a logarithmic function, medium priority requests used a constant function, and high priority requests used a polynomial function. To test this algorithm, we have written a scheduler in Python. When comparing our results to the output of a static schedule optimization algorithm, the overall ride time of requests decreased by 30% due to less interleaving of request pickups and drop-offs. This benefit can be seen for all requests, with higher priority requests receiving more improvement. I would like to thank Dr. Sukapati, Dr. Smith, Ms. Burson, Dr. Dolan, and the RIS program for their support this summer. I would also like to acknowledge the National Science Foundation for funding this work. Thank you.